All right. Now, what you'll notice is that even though I cannot get rid of this boundary condition by setting my v, I actually know the other part of this boundary term, du dx, right? That's actually exactly my boundary condition, du dx equal to a at x equal to 0. So this part is actually a, right? Okay, so instead of getting rid of the boundary term, we actually have a boundary term that is it somehow also uses the boundary condition. So let me just write this in a slightly different way, in a way that is similar to what the kind of weak form we derived before for the fixed boundary conditions, for the Dirichlet boundary conditions. This, which I basically flip the sign, would be equal to this term, vf dx. Then what I have is minus v0 times a. All right, so this is new. This is the new item in the weak form because of the boundary condition. And now what we have to do is we have to discretize the weak form in a different way. And okay, so remember when we plug in the different v's, different v's into v's and expand u, this part becomes my matrix aij times the value of u at, actually now I have to aij, I and j goes from 0, right, to un minus 1. So I have this, and on the right hand side, now what I have is I have my, again, b0 all the way to bn minus 1, but then there is additional term. This additional term is v0 times a. And remember what v is here. For the different equation, v is equal to phi0, phi1, etc., right? So when v is equal to phi0, what is phi0 at 0? Phi0 is this function, right? Okay. Yes, phi0 is equal to 1, okay? And how about phi1? How about phi1?
0.
Yes, 0, right? Phi1 is this function here, and phi2 is this function. So phi2, etc., are all equal to 0 at the left boundary. Okay, so basically what I have is one additional vector, that is a 0. Okay, so that's what I have as an additional boundary condition. That's the impact of the boundary condition. Again, it's something additional on the right-hand side. The difference between this case and our previous case is that the number of equations are different, right? So if you go back to our previous Dirichlet boundary condition case, my unknowns goes from 1 to n minus 1. My right-hand side is 1 to n minus 1, right? But in this case, my unknown is actually expanded into from 0 to n minus 1. So let's see how that plays out in our code. All right, so now in our code, I actually have to do something a little bit different, even for the diagonal. Okay, my I has gone from 2 to n elements. I have computed aij, but if I do this and you can look at my a, I have only filled starting from here. So I also need now this term, the very first term, right, in order to solve, no, that's not what I want, in order to solve also for the first unknown, u0. So what is a00? Let's go back to our code. So a00 would correspond to integration from 0 to 1, d phi 0 dx squared. Okay, and phi 0 is different from the other elements in that it is only non-zero in one element as opposed to the other basis functions which are non-zero in two elements. So that if you work out the math, it's actually the same that as the other integrals, but there is only one term as opposed to two terms, and that is x1 minus x0, which is 0. Okay, so that's what a00 is. It essentially only have this term. Okay, let me add it. x2 minus x1. Okay, so if I run it, now I have my variable a also filled in here. So that would be my updated matrix. And then, so here I have worked out the off diagonals. So if I do it, I have filled in, yeah, both here and here. So I already have these entries filled, right, by symmetry. Okay. So so far so good. We have our A, and our right hand side also needs to be updated. So this is trying to compute. So okay, so here I shouldn't exclude the first entry, right? So my first entry is still like this, and I won't need this anymore. So I'm excluding the last row and last column because my last degree of freedom is still fixed. That's still the old boundary condition, but the first degree of freedom is now unfixed. My B is like that, and here I have to go from so this formula still applies, but then my B1 has to be only half of. So remember, when we are looking at B, we are integrating over a triangle, right? But in when I have the first element, I have to have x2 minus x1 divided by 2, right? So the base times height, which is 1 divided by 2. Okay, and my B also starts from 1. So now I don't have this anymore. And to solve, I have a backslash b, and I also have to change this. I minus of the left boundary condition. Okay, minus. Let me actually just change b, so that let me update b. B1, so that's the only term I need to update, is equal to B1 minus my derivative on the left. So let's say 1 is the derivative I want to set on the left and see how it goes. All right. And when I have the u, I no longer need to specify anything on the left because u already includes the solution on the left. And I still set my right boundary condition to be 0. So let's see how it goes. The u exact also needs to be updated. I think the derivative is going to be 0.5 naturally, which means I need to add 0.5 times x fine to make it work.